Good morning to all of you again. Today, within this lecture, we will further move on, or we will further dive into the topic by considering a truss problem or linear elastic bar. So today we will be focusing on deriving a stiffness matrix for a linear elastic bar. So we will be using the same general concepts which we learned, which we applied for when we're analyzing a spring. After deriving a stiffness matrix for a linear elastic bar, or we call it a truss element, then we will be moving on we will be discussing about transformation matrix. How do we map the local reference frame to the global reference frame? What is the mapping key? So in this case, transformation matrix is what maps the local coordinate, the information available in the local coordinate system to a global coordinate system in two dimensions, as well as in 3 dimensions. We will be looking at both, 2 dimensions as well as 3 dimensions. But first of all, we will look at a 2-dimensional problem. Then after we have the transform matrices in the global coordinate system, then we can start assembling the process. We can assemble all the element stiffness matrices to come up with the total global stiffness matrix. Okay, all of these steps will be done by considering a truss element or truss assemblage today. When we move on, you will realize it is nothing but the same which is applied for a spring element, but it's only only certain terms based on the physical properties, based on the physics of the, let's say, truss will change, and it is the same protocol that you have to follow whenever you are deriving with irrespective of the element that you're considering. So let's consider now the derivation of a stiffness matrix for a bar element. First, let's focus using a local coordinate system. So first, what is a bar, or what is a plane truss? We call it a linear elastic bar or a plane truss. You must have definitely seen this overhead bridges, overhead railway bridges. They are mostly connected using trusses or truss assemblages, so that the forces, because these are distributed forces, that will so you need structures such as trusses to support these moving or dynamic loading conditions. So trusses give an understanding about the basic principles applied in structures. So that is the motivation that we will start using a structural or truss element, because it's a fundamental component of large assemblies. So without further, let's say, taking time, truss, let's try to first understand what a truss is. A truss element is a linear elastic element which has a constant cross section. So here I have shown a truss element. This is a truss element, linear elastic truss element, subjected to tensile forces given by, so it is under tension. So this is in 1 dimension. Of course, if you look at from the other side, that is in this direction, the end elevation, there will be a cross section. Let's call it this truss has a cross section of A. Yeah, so it has a constant cross sectional area. We call it a prismatic bar element. These trusses are mostly pin connected trusses, and these are subjected to tensile and compressive forces based on the location which is applied in the total truss. So first, when we consider this truss element, we will arbitrarily place it in, let's say, 2 dimensions. Yeah, and just like in the previous case, let's assign a local coordinate system. So the local coordinate system for this truss is x hat and y hat. This linear elastic bar element is arbitrarily placed in 2 dimensions. So the local coordinate system, we can divide it as one axis which goes along the linear elastic bar given by x hat, and in the orthogonal direction, in the perpendicular direction to the length of the axis, you can define y hat. And now we define a global coordinate system, which is given by x and y. Yeah. So you may ask now, okay, why do we need a global coordinate system? Because we have a because we are considering one element. Of course, the significance of a global coordinate system won't come, because you can have your reference. I mean, like, the global coordinate system and the local coordinate system can coincide if you are considering a single element. But when you are analyzing a spring bar assemblage or truss assemblage, the structure can be complicated, isn't it? So then you have to consider the overall structure and assume a global coordinate system. So in this case, the global coordinate system has rotated by 30 degrees with respect to the local coordinate system. So in this case, the local coordinate system has rotated 30 degrees anti-clockwise direction. So this is again subjected to tensile forces. That is what I have mentioned here, the two tensile forces which try to stretch the prismatic bar, and the length of the bar element is so I will be calling this a truss sometime, a bar, or a linear elastic element, bar element. So all this refer to a truss element, okay, in this case. So the bar element has a length of L, and it has two nodes, 1 and 2. The forces, the local forces acting on node 1 and 2 are defined by x1 hat and fx2 hat. Yeah, and the displacements at node 1 and 2 in the local coordinate system are d1x hat and d2x hat. So when we consider the bar element, there are certain properties. The cross-sectional of the bar is considered to be A, and E is the modulus of elasticity, L is the initial length. Of course, d1x hat and d2x hat are the longitudinal displacements along the length of the bar. Yeah, you may ask, what about the lateral distribution, or what will happen in the y direction? For the moment, let's consider them, the displacement as well as the forces are zero. So there are no forces acting on in the y direction. Of course, let's the bar cannot sustain a shear force or bending moment. Let's assume that for the moment, but and go ahead with the derivation, but it will not make much difference, you will see. So to start with, let's first apply what we know. We know the principle of Hooke's law. So we need to Hooke's law. We know the relationship between the stress applied in the bar and the strain is given by this relationship. Sigma x is equal to the Young's the elasticity modulus times the strain in the x direction. So you can further write the strain or the strain relation with respect to the displacement. So we started with the stress, and we are analyzing the strain now. The strain can be written as du hat divided by dx hat. Dx hat kind of like the for that particular direction, let's consider it to be the initial length, and u hat gives the displacement function for the particular direction in this case. So if we consider, let's say, the force equilibrium, we know the bar is subjected to a tensile force, and the force is nothing but the stress applied in the x direction times the cross-sectional area, so which is a constant. And this bar is loaded at the two ends. So we have a relationship now. We have related the stress in the bar with the corresponding material properties or the geometrical properties to the forces applied in the bar. So we can use this equation B, the strain relationship, and substitute in equation A. Yeah. So to obtain a relationship for the stress applied in the x direction with respect to the displacements. So this is what you would end up. That is, you would end up in getting equation D, where the stress is proportional to the strain. So simplifying again now, we can, since we know the relationship between the stress and the force applied or the tensile force, let's try to remove the stress term here and use the tensile force in the equation. So you get the equation D and substitute with the equation C, so that we take away the stress term, and what you would get is that now directly the forces are, the tensile force is expressed in terms of the strain or displacement. As a trick, let's say the mathematical trick, you will realize as to why we do it. Let's take the derivative of equation E and let's try to differentiate with the x hat. Yeah. So you take this total function here and you try to differentiate with the x hat. On the right hand side, obviously it will become 0 because it's not a function. And for the moment, you can differentiate this whole left hand side with the x hat, but obviously, of course, in this case we have assumed that A and E are functions of x hat, but for the current case, let's assume that the cross-sectional area and the modulus of elasticity are constant, and we can take it out on the left hand side when you differentiate. So what do we end up? Of course, you will see what we will get. But let's, in this context, when we arrived at equation E, we have made certain assumptions, as I mentioned before. So in order to derive the element stiffness matrix for a bar element, we have considered certain assumptions. The first assumption is that the bar does not undergo any shear force or any bending moment in mathematical terms, meaning Fy1 hat is and F2y hat are 0. And of course, bending moments at 1 and 2 nodes, first and the second nodes, are 0. And any effects on the transverse displacements are ignored. That is, only we are considering the displacements and the reactions, of course, in the longitudinal direction. And of course, we are considering a linear elastic spring element. So the Hooke's law is applicable. And it is the bar is only subjected to n loads, or there are only n loads applied. There are no distributed loads applied. And we will be looking at the distributed loads later onwards when we move on with, let's say, when we further analyzing trusses and when we complicate the issues, you will see how we can deal with distributed loads. You will most likely work on the distributed loads also in the lab classes, but it's quite simple. It's the same principle which is applied. So yeah, now let's try to apply these 7 odd steps that we learned in the previous lesson, where we used to derive the stiffness matrix for the spring element. So the first step which we did for the spring element, to select an element type. Yeah, so there we selected a spring, but here we selected a linear elastic bar. Okay, the step 2 is nothing but to select a displacement function which describes the displacement at the 2 nodes. In this case, of course, 2 nodes. And here, just like in the case of the spring, we have used a linear equation or linear relationship to describe the displacement function, where u hat is equal to a1 plus a2 hat. So we need to find, let's say, two coefficients, y2 coefficients. The number of unknowns in the displacement function is equal to the number of degrees of freedoms in the element. So in this case, we have 2 degrees of freedom, one at node 1 and one at node 2. So there are two unknowns. So similar to the spring element, I will not derive this again. I will be using the equation which we derived in the previous lesson. You can, once you apply the relationships and the, let's say, the properties of the spring, or in this case, the bar which you are using, you would end up in getting the displacement function using, of course, the displacements which takes place at node 1 and node 2. This is the same relationship which we obtained for a spring element. Yeah, nothing different. So once you have the displacement function, you can neatly arrange it in the matrix form. You can neatly arrange it in the matrix form and obtain this relationship, or these, let's say, the so-called shape functions, which attribute to the displacement in the local coordinate system. Good. So now you have derived, we have derived, let's say, we have assumed a displacement function which takes place, which can describe the displacement throughout the domain that we are interested. So this is the spring element we consider, which is rotated by theta degrees with respect to the global coordinate system. So the local coordinate system is rotated by 30 degrees anticlockwise. And the displacement function, which describes the displacement within the domain of the element, bar element, is given by the u hat function. Here at node 1, you would see there's a d1x displacement, and in here d2 and node 2, there's a displacement in given by d2x hat, and it is continuous. That's nothing discrete or no change. It's simply a linear function. Although I have just drawn the displacement on the y direction like this is for y hat direction. This is for you to get a general understanding. I have just superimposed the displacement which takes place in the x direction. Okay, so at node 1, this is the amount, the displaced amount which the bar undergoes, and at node 2, this is the amount that the bar is subjected to, and within the element, whatever, and in an arbitrary point, since you can interpolate it and get it, we call it an interpolation function also. So within the bar element, the displacement we can be described by the u hat function. Yeah. So step 3. Now we have to relate the displacements to the strains and stresses. So let's call step 3 as defining the strain relationship to the displacement and the stress, and applying the stress strain relationships. So the strain in the x direction, as I mentioned, can be written by the derivative between the displacement function and the coordinate system, in this case du hat divided by the x hat, which is nothing but, yeah, the initial length of the bar L and the total displacement which the bar experiences. Yeah, the total experience is the total elongation is nothing but d2x hat minus this part d1x hat. This is the total deformation which the bar undergoes. So 3.15 equation explains the relationship between it basically uses the nodal displacements and the material property, let's say material geometry, and which relates to the strain. And the stress can be applied, of course, since we by the Hooke's law. So in step number 4, now let's try to derive the element stiffness matrix equation. We know the tensile force is nothing but the area of the bar times the stress in x direction. So we can use the information which we obtained from equation 3.15 and 3.16 and substitute in 3.17, so that we can eliminate, or we can substitute the strain term and express in terms of the nodal displacements which we obtained here in this equation. Yeah. So T, the tensile force, is equal to the cross-sectional area times the elongation times the modulus of elasticity times the total strain of in the x direction, which is given by this term. So we can apply based on the sign convention. We know now the forces, since when we consider node 1, let's go to the original figure here. When we consider node 1, this is subjected to tensile force, and we have defined F1 x hat positive to be on this direction, and tensile force is on the other direction, isn't it? But when we consider node 2, F2 x hat and T at node 2 have the same sign. So keeping that in mind, let's apply now the sign convention at node 1. So minus T, F1 x hat is equal to minus T. We can do a substitution now. You can substitute this equation 3.1.9 into 3.1.8 previous, and apply the sign convention, of course, and we can take around the tensile force or substitute the tensile force, and what we would end up is getting a relationship which is explained by this equation. Similarly, you can do the same thing for you can apply the same concept to node number 2. Node number 2, F2 x hat is equal to, now the sign is positive because the tensile force is positive here, and you can describe it now using the nodal forces in the local coordinate system. You have nicely obtained two equations for the nodal forces acting in the local coordinate system, acting at node 1 and acting at node 2, and you have now obtained it using the local coordinates, local displacements of node number 1 and 2. Now it's nothing but arranging these two equations in the form into the form of a matrix. What you would end up is, on the left hand side, you segregate or write a column. You have the you can define the force column matrix in the local coordinate system, and when you write down the local displacements as a column matrix, what you would end up in the middle, let's say, is the stiffness matrix for an element, for a bar element, very similar to the one which you obtain for a spring element. In the spring, you obtain this, of course, you express this in terms of the spring constant, but here the spring constant is kind of like this term AE divided by L, isn't it? So other than that, it is basically the same thing. So what has happened is, now the material properties of the bar has gone inside this matrix. That is, other than that, all the other concepts are almost the same. So the stiffness matrix, we call it an equivalent stiffness. Of course, we can call this stiffness matrix for a bar can be expressed using k hat. Now we are still in the local coordinate system. Is nothing but A divided by L, and when you take, since you take out these terms, you would get a symmetric matrix where off diagonal terms are minus sign, just as in the case of a spring. So here I have mentioned AE divided by L is quite analogous for a spring, having a spring constant of K. So step 5 is nothing but assembling the element equation to obtain global or total stiffness equation. So we have a stiffness equation for one element. Yeah. So there can be several stiffness equations based on the number of elements you define in the problem. Now what you do is you try to map them into the global coordinate system first of all, and then in the next step, after mapping, then you can sum them up together, isn't it? You can sum all these element stiffness matrices using the direct stiffness method, which is quite easy, which we learned in the previous lecture, and relate it to the global forces acting on the structure. Once you apply this, once you assemble these element stiffness matrices and express in terms of the global coordinate, total global stiffness matrix, you can solve for the nodal displacements. And of course, if after when you apply boundary conditions, you can solve for the nodal displacements, nodal unknown displacements. When you have nodal unknown displacements, then you can further zoom into the assembly and consider the stresses as strain where the elements are subjected to. So you can do your analysis in an element level once you find the nodal forces. So it's all about back substituting your unknowns into the equations which you derived, the element equations which you derived, and you can find the forces acting for of each element and the stresses, so on and so forth. So it's quite straightforward. So let's call this an example 3.1, and for the bar assemblage which is shown here in this figure, you are supposed to determine, so there are three bar elements which are interconnected, and so we can identify 4 nodes, 1, 2, 3, and 4. Node 1 and node 2, that are the both ends are connected to, let's say they are fixed, they're connected to fixed supports, and node 2 is subjected to an external force of 3,000 pounds. Yeah, and each bar element has an initial length of, let's say, 30 inches. In total, the structure has a length of 90 inches, and the material properties of element 1, 2, and 3 are given in this table. The modulus of elasticity is given on the second column, and the cross-sectional area is given in the third column. So what is your task? Your task is to first to find the global stiffness matrix for this for the truss assembly. Once you find the global stiffness matrix, you need to find the displacements at node number 2 and node number 3. Obviously, the displacements at node number 1 and node number 4 will be 0 because they are fixed. And once you find the displacements at node number 2 and 3, the next task is to find the reactions at node number 1 and 4. Even though the displacements at node number 1 and 4 are 0, there will always be reactions because they are fixed supports. So you are supposed to find the reactions at node number 1 and 4. So based on these boundary conditions and based on this problem, try to take a few minutes and try to work out this problem. Our first task is to find the global stiffness matrix. Before we find the global stiffness matrix, we need to write down the element stiffness matrices, of course, in the local coordinate system. For that, we have to analyze element by element. So let's try to find the element stiffness matrices using the equation 3.1.14, which is nothing but this equation, which describes the element stiffness matrix for a bar element or a truss element, of course, for a linear elastic bar. So there are 3 elements, 1, 2, and 3. 4 nodes, 1, 2, 3, 4. For the first element, which is, and the second element, we see there are identical material properties, of course, and of course, geometric property. E and A are the same. So we will write K1 is here. I have put brackets in the superscript, meaning the element which I'm when I use this notation, I'm trying to refer to the element which I'm considering at the moment. So element 1 and element 2 has the same stiffness matrix. Cross-sectional area multiplied by the modulus of elasticity. Of course, you have to take into units now in this case. So I will be using the imperial units in this case, in this particular example. So 30 is the initial length. 30 inches here, and you write down nothing but the stiffness matrix, which is a asymmetric matrix where the off diagonal elements are -1. You can simplify this equation to obtain this, express the term element stiffness matrix in this manner. And for the clarity, because we are going to construct the global stiffness matrix, let's try to write down the corresponding nodal displacements for this particular spring, particular bar element. So if we consider element 1, the corresponding nodes would be 1 and 2. So similarly on this side also, on the right hand side, that is in the column wise also, you can write 1 and 2. I have not written here, but you can directly, you can understand, isn't it? So you can write it as 1 and 2 here for element again 1. It's the same thing. So if we consider element number 2, the corresponding nodes are node number 2 and node number 3. Yeah. So similarly, we can consider the element number 3, which is this one, element number 3 over here. And the corresponding nodes are node number 3 and node number 4. So K, and within the parentheses, we write 3. The cross-sectional area times the modulus of elasticity divided by the initial length. And this is the equation which we derived for a linear elastic element, linear elastic bar. You take out the common factor out and write down the element stiffness matrix. And of course, you can write down the corresponding nodes, which will be helpful when constructing the global stiffness matrix equation. So now it's all about assembling the element stiffness matrices using the direct stiffness method. What do we get? We get capital K. We move from simple K, which is defined for an element now. We move to, we now try to obtain the global stiffness matrix, which we define by capital K. Now we have also omitted the hat sign because in this problem, we consider the global coordinate system as well as the local coordinate system aligns, and x hat can be replaced by x now because there is no rotation. Of course, you will learn this. I mean, you will see it's the same coordinate system that we are talking about. Even we talk in terms of hat sign when we are talking considering the local coordinate system as well as the global coordinate system. So we have 4 nodes. Yeah, 4 nodes means we have 4 degrees of freedom. So the rank of our matrix would be for a 4 by 4 matrix. The stiffness matrix we can write in this way. Yeah, so we have a common factor 10 to the power 6. We can take it out here. And now we can write, so without filling these information which are in the middle, we can write the corresponding, let's say, the displacements as a row as well as a column. Then you can simply start assembling using the direct stiffness method, which I explained in the previous case. So if we consider d1x by d1x, we have only one term. Yeah, because here d1x and d1x is only this term which is present here. So you simply write that value. So if likewise, you can start assembling the constructing by summing up the corresponding elements of the element stiffness matrices to develop the global stiffness matrix. Just to recap, let's try another element where we have 2 components. We have, if we consider the corresponding elements for the location d2x and d2x, that is in node number 2, how many elements do you have? According to this, we have, so this one 2 by 2, this is again 1 element, and here 2 by 3. Of course, This is again another element. So these are the two components for the corresponding elements. So we can simply sum them up here at the corresponding location. What we get is 1 plus 1. Yeah. So I think this method is clear now, and you can further use this to obtain the other, let's say, elements in this global stiffness matrix equation. Yeah. So what you would end up is getting a nicely, let's say, constructed 4x4 matrix where you have added up the corresponding elements for considering the element stiffness matrix equation. Since you have now the global stiffness matrix constructed for the spring assemblage, or for the total assemblage, then you can use this to relate it to global nodal displacement as well as global forces. Yeah. So here we can write it using this equation. So the total force applied on the structure is nothing but the global stiffness matrix multiplied by the displacements, the nodal displacements of the structure. So on the left hand side, you can write down directly the global forces applied, and on the right hand side, you have the displacement vector, the global nodal displacement vector, which is related via the global stiffness matrix. The next step, simply what you do is you apply the boundary conditions. What are the boundary conditions we have? We know the displacements at node number 1 and node number 4 in x directions are 0. So simply these two terms would be 0. Yeah. So we can simply extract the corresponding matrix within this total matrix system, because whatever the terms which get multiplied using this term and this term would be 0. So we can simply extract a sub matrix of this total stiffness matrix, total global stiffness matrix, and apply the boundary conditions. Yeah. So we can extract this sub matrix because it corresponds to non-zero displacements here, which is of course related by f2x and f3x. Simply what I have done here from here to here is simply extracted these terms, the non-zero terms. Okay, we have applied the boundary conditions so that we apply the non-global forces, and considering the previous equations, we have obtained, if we consider the node number 2 and node number 3, the node number 2 is subjected to 3,000 pound force, and in node number 3 there are no forces, external force applied on the structure. And this is the extracted matrix which I have written here, and the corresponding non-zero displacements are d2x and d3x. By solving this, you would be able to get answers for the nodal displacements at node number 2 and node number 3 in x direction with respect to the global structure. Of course, these are global displacements. Once we have the global displacements at node number 2 and 3, we can simply back substitute them and try to obtain the reaction forces at node number 1 at node number 4. So again, using this matrix, yeah, you can use this first column and the last column. Of course, some components would be 0, but you know the displacements at d2x and d3x. When you substitute these values, simply, but this is nothing but simply solving algebraic equation, you would get the reaction forces at node number 1 and node number 2 to be minus 2,000 pounds at node number 1 and 3,000 pounds at node number 2. Just for you to clarify whether you have got the answers correctly or whether you have made a mistake, you can still obtain the non-nodal forces, the non-node applied loads, using the answers which you just obtained. So F3 should ideally be 0 because there's no applied force, Now you would realize when you substitute the answers which you have got here, d2x and d3x, you would end up getting a 0, which means your answer is correct. Yeah. Another cross check is, okay, using these values, you can obtain the answer at node number 4, the reaction force at node number 4. How you can again validate your answer, verify your answer is, you try to consider the force equilibrium. What is the force equilibrium? You know the total force applied on the structure is 3,000 pounds at node number 2, and the total reaction forces are equal and opposite, of course, which is given by F1x plus F4x. F1x is minus 3,000 and F4x minus 2,000, and F4x is minus 1,000, and when you sum it up, you would get minus 3,000. Of course, minus sign means it's the opposite direction, and you know at node number 3 there are no external applied forces. So now you see the equilibrium of the assemblage is verified, which indicates that your answers are correct. So it's also important to note that the corresponding external forces are also obtained using the forces or the displacement which you obtained. So this is a good indication that you have arrived at the correct answer. In this section, where we're talking about transformation of, let's say, vectors in 2 dimensions, we are nothing but we are doing, we are applying the same principles, but we are trying to map the global coordinate system to a local coordinate system now in 2 dimensions. Yeah. What is the motivation? Always the motivation is to construct the global stiffness matrix, the total global stiffness matrix for a total structure based on the element stiffness matrices equations derived for element stiffness matrices. So the road which we get from the element stiffness matrix to a total global stiffness matrix is via, first you get the element stiffness matrix for a single element or for all the separate elements you have in the system, and you try to construct the global stiffness matrix for a total structure. But now the global stiffness matrix can have, let's say, it can be defined in the local coordinate system. Now you need to transform the global local coordinate system or the stiffness matrix defined in the local coordinate system to the global stiffness equation. So this is the link that we are talking in this section, how we can do the transformation, because all this time we were talking about problems where the global coordinate system was coinciding with the local coordinate system. But now in this case, what if there's a rotation between the 2 coordinate systems? In the previous sections, we just simply skipped it, but now let's try to address this. So for this, let's consider simply a vector D, which can be which is not, of course, coincident with the local coordinate system or the global axis, simply a vector D. Our aim is now to relate the global representation or the global displacement components to the local displacement components. What is the relationship? What is the transformation matrix where we can transform the local coordinates to the global coordinate systems directly if there's a rotation, or if the 2 coordinate systems have let's say a rotation component, or let's say they are not coinciding with each other. So we say our aim is to develop a transformation matrix to obtain, let's say, global stiffness matrix for a bar element. So we consider a vector D, of course. If we express in terms of the global coordinate system, we can write it if, and we are only now in 2 dimensions. So we have 2 unit vectors I and j, which are multiplied these by coefficients dy x hat and d2y hat. These are the displacements defined in the global coordinate system in the x and y direction. The same vector can be expressed using a local coordinate system, which is given by I hat and j hat. These are the unit vectors in the I hat and j hat direction. And the corresponding displacements are dx hat and dy hat. So this is the same thing, same vector explained in 2 different coordinate systems, nothing new. Okay, quite simple. So I and j are unit vectors in the x and y direction. I hat and j hat are the unit vectors in x hat and y hat direction. So this is here I have mentioned now the difference between the local coordinate system and the global coordinate system. Now the global coordinate system, yeah, is rotated, let's say anti-clockwise or clockwise, let's say theta degrees with respect to the local coordinate system in this case. Yeah, so this is vector d that we are planning to, vector d we have expressed, this vector d we have expressed in terms of the local coordinate system as well as the global coordinate system. Yeah. So now what we can do is we can establish a relationship between these 2 coordinate systems using, let's say, certain coefficients. Yeah, let's define a unit vector. So let's consider this ith unit vector defined in the x direction, jth unit vector defined in the y direction, I hat in the x hat direction, j hat in the j hat direction, and this unit vector can be explained. Let's say, let's try to express this unit vector using 2 subvectors which are orthogonal to each other, of course. One in the direction of I hat or x hat direction. This is, let's call it an a hat, sorry, a underscore, or underscore is because I am referring to a vector. A, using a and b vectors, we can express the ith unit vector. So these are, let's say, these are perpendicular to each other, of course. A under a vector and b vector, we can say the unit vector is obtained or we define such that the sum of a and b gives the unit vector I. This is quite clear, isn't it? Yeah. So considering the, let's say, cosine laws, yeah, you know, you can obtain a th vector in terms of ith unit vector. What is a now? Because this is perpendicular. A, the magnitude of a is nothing but I, magnitude I times cos theta, because this angle here is not, this angle here is theta. Yeah. So magnitude of a, vector a is I times cos theta. So since I is a unit vector, the magnitude of I is 1. So you can obtain the magnitude of a when you substitute in this equation. That magnitude of a is nothing but cos theta. Agreed? Similarly, you can do the same thing to express b in terms of the ith vector, and what you would end up is getting is the magnitude of b is nothing but sine theta. So now you have obtained the a and b vectors, or the magnitudes of an a and b vectors in terms of the rotation angle, that is the theta value. So we also know that a is in the direction of I hat and b is in the direction of minus j hat. A is in the direction of I hat and B is in the direction of minus j hat here. So we can simply write again the vector A using the unit vectors in these directions. The unit vector in the I hat direction multiplied by the magnitude. Since we already know the magnitude of A, which is equal to cos theta, it is simply A vector can be expressed as cos theta times I hat. Yeah. Similarly, B vector, it is now in the opposite direction of the jth vector or j hat vector. When you multiply the magnitude of B with the unit vector, you would end up in getting the B vector. So we know B is equal to sine theta, and you would end up getting sine theta times minus j hat. When you substitute equation 7 and 8 back into equation number 2, that is this equation, our initial equations where A plus B is equal to I, since we already know A and B in terms of the other local coordinate system or the local coordinate system, that is I hat and j hat, we can express I to be I hat times cos theta, j hat times sine theta, but of course there's a minus sign. Yeah. So you have found a relationship between the ith vector O defined in the global coordinate system as well as I hat and j hat defined in the local coordinate system, which is quite good because we want to find the relationship between the local coordinate system as well as the global coordinate system. Similar way, you can do the same process to find the relationship, or we can define in the, let's say, define the jth vector in terms of a hat and b hat, and find the relationship or obtain a relationship between the local or describe j hat in terms of I hat and j hat. So you can define jth vector using I hat and j hat, that is the global coordinate system can be related to a via the local coordinate system, just like the steps that we just followed in this process. So a hat and b hat is equal to nothing but j based on the definition, and just like in the previous case, using the geometry, we can write a hat and b a dash and b dash. Yeah, so we can use this equation number 10 and 12 and substitute in equation 10 to express j in terms of I hat and j hat. So using equations 9 and 13, that 13 is this and 9 is nothing but the relationship in terms of the ith unit vectors as well as I hat and j hat, we can back substitute all these I and j vectors which we obtained, these the expressive unit vectors, back into equation number 1. Can you remember the equation number 1, which is nothing but the expression for dth vector in the the global coordinate system as well as the local coordinate system. So since we have found I and j values now, we can use this, we can substitute these values which we obtain for I and j to obtain a value for vector d. So d is nothing but dx times the I hat sign, where ith vector, where you substitute this value, dy times jth vector, and it is equal to whatever the values we define in the local coordinate system using I hat and j hat. By combining the like coefficients, because in such equations we can combine the coefficients, the coefficients corresponding to I hat and of course, on the left hand side and the right hand side, and of course we can combine the coefficients corresponding to j hat. What you would end up is, if we consider this equation 14 and only consider the ones corresponding to I hat sign, we can write d cos theta plus dy sin theta. Yeah, the terms corresponding to I hat, dx is nothing but d cos theta plus d sin theta. Then in the next term, you can find the similar terms or combine the terms corresponding to j hat, which I will use this color. J hat is this term, this term, and this term. So dy hat is equal to dx times sin theta, of course the minus sign because there's a minus sign here, and on the in the next figure you have, of course, dy times cos theta. Yeah, so now you have obtained two equations, and if you now explain this in terms of a matrix, you separate the ones relating to the global coordinates, local coordinate system with that of the global coordinate system, and you would get a neat equation like this expressed, which gives the relationship or the transformation or the rotation, you call it the rotation matrix, which defines the relationship between the local coordinate system as well as the global coordinate system, where C refers to cos theta and S refers to sin theta, and the theta is measured anti-clockwise from the global coordinate system in this case. So equation 16, we can say, relates the global displacements to the local displacements. That is, it relates D to D hat. This is called the rotation matrix, or in other words, the transformation matrix, which because it transforms the local coordinate systems to the global coordinate system. So we know we have transformed the displacements. We have considered displacements and transformed them from the local coordinate system to the global coordinate system. Yeah, which is quite interesting. And now let's see whether we can use this in another example, let's say to solve more complicated problems. And now we know for each element, for each bar element, we can define the stiffness matrix in the global coordinate system. Yeah, for assume now you have several elements. For each element, now you can define the global defined stiffness matrices in the global coordinate systems. I think now you get the idea as to where we are aiming at. For each element, we have now element stiffness matrices, as well as we are able to express the local coordinates or local displacements as well as local forces in a global coordinate system. In the next step, we are now zooming out. That means we are considering the total structure. We will be using the direct stiffness method and try to construct the total stiffness matrix for the whole total global stiffness matrix. Let's say for the for a bar element. First, in the first place, let's consider the rotation and try to construct the global stiffness matrix for a bar element. Recall, we just derived the relationship between the local displacements as well as global displacements in two-dimensional space using the rotation matrix. Now, for obtaining the global stiffness matrix for each component, we can use this equation which we derived, and in the next step we will assemble the global stiffness matrices for each component to obtain the total global stiffness matrix for the total structure. That is the aim. So for the bar element, which we just derived in the local coordinate system, we can write, if you can recall, for a simple bar element, which has two nodes, the forces applied and 1 and 2 can be expressed using the hat sign, and the local nodal forces can be expressed using the d hat signs, which is related via the stiffness matrix for the bar element. It is nothing but f hat is equal to k hat times d hat. So now the aim is to relate the global nodal forces, that is F, to global nodal displacements D. Yeah. So if we consider a bar element, which is arbitrarily oriented with respect to global axis, and we know it is related via the global stiffness matrix equation. So if we consider a bar element, now we are trying to express in the global coordinate system. Take away the hat signs, because now we are talking about the global nodal forces applied for the bar element. We are taking away the hat sign because we are talking about the global nodal forces at node number 1 and node number 2, which is related via the global stiffness matrix for that particular bar element. Yeah. So you can express this total matrix, which has, of course, 4 by 1 matrix for the column matrix, for the force matrix, and again 4 by 1 matrix for the displacement matrix. So recall the transformation relationship for d1x, yeah, which we obtained using this equation. We know d1x hat can be expressed using d1x and d1y. The local coordinate system can be expressed in terms of the global coordinate system. The local coordinate system can be expressed in terms of the global coordinate system using the transformation matrix which we just derived. Similarly, for the x component in the node number 2 can be expressed using the same transformation. Yeah. So now for the, at this moment, yeah, at this moment, let's yeah, to keep simple, keep the thing simple, let's consider these two terms which I have just mentioned. What I'm trying to show is how we can expand the matrix in so that we come to the rank of the global stiffness matrix. Yeah. So we are interested in displacements in the x direction as well as y direction in the local coordinate system, which can be expressed via the nodal displacements in the global coordinate system using this relationship. So this is nothing but I have transformed these two equations into a matrix formation. Yeah. So the corresponding elements, of course, the other elements you can see there are zeros wherever the nodal displacements does not have any effect on the local displacement. So nothing but I have transformed equation 5, or written down the equation 5 in the form of matrix. In terms of, let's say if you use letters, we can say d1 hat is related via a transformation matrix. Let's call this t hat times d. T hat is nothing but the transformation matrix expressed in terms of sines and cosines. Similarly, we can also, unlike the displacements, we can also transform forces in a similar way. We can use a similar same transformation matrix because we are moving from one coordinate system to another coordinate system. So it is the same principles apply for the nodes or nodal displacements as well as the nodal forces. We can express the forces applying in one x directions at node number 1 and node number 2 using the forces applied at node number 1 and 2 in the global coordinate systems via the transformation matrix. So it is the same thing which is applied for the force transformation also. The force transformation is very similar to the displacement transformation. You can see, simply you move from one coordinate system to the other coordinate system. So where are we going at the moment? We can simply use equation, of course, we can use equation number 7, that is the expression, the relationship between the global coordinate system as well as the local coordinate system, the displacement relationship, and use this in the force equation, or we can use this equation in this. So in this, rather, in this equation, to obtain the relationship between the local forces, now I have simply substituted d hat using these two terms. Yeah, d hat is equal to t transform times d. So here you have the k hat matrix. Of course, you have used the equation number 2. Yeah, so I have used equation number 2, and I have used equation 7 to take away the d hat sign. So d hat is equal to, so d hat is equal to t transformed d. So you would end up in getting equation number 11. Once you have equation number 11, you can substitute by in equation number 10. Here I made a mistake. So you simply consider equation number 2 and substitute the equation, the values you obtain using equation number 7, and of course an equation number 10 to obtain this equation number 12. So I have used equation number 11 and substituted f hat by t transformation multiplied by f, which is equal to the right hand side of this equation, k hat times d hat times d. So now our objective is to find f. For this, we need to invert this matrix, or we have to for inverting t, it should be multiplied. For first requirement is that t matrix should be a square matrix, otherwise we cannot invert this matrix. So in order to make this transformation matrix a square matrix, we need to expand d hat and f1 hat as well as k to the order consisting, which is consistent with the global coordinate system. Yeah, so what do we do? This is our transformation matrix for a single element in the x and y direction. Of course, we can now expand this transformation matrix to the global coordinates, also to the rank of the global coordinate system. So in equation 313, you can see this is nothing but I have expanded it to a global coordinate system. The hats are included here. The x and y terms, the x and the y terms are placed on the right hand side, and you can see this is the same matrix included here. The remaining parts, whatever the non-contributory parts, are 0. They are corresponding to 0. So these terms which corresponds to node number 2 here in this case are 0. And whenever we consider node number 2, the corresponding node number 1 contributions are 0. So in simple terms, you can express this equation as d hat times the transformation matrix times the displacement matrix in the global coordinate system. So this is nothing but, again, the relationship between for a bar element in the local coordinate system, which relates the local coordinate system to the global coordinate systems via the transformation matrix. Similarly, you can write down the transformation for the forces. It is the same because you are moving from one coordinate system to another coordinate system. So the transformation is similar. Here I have expanded this transformation matrix. Of course, um, we know we can use the equation number, let's say what? Equation number, there's a lot of equations. Yeah, equation number 2 to write the global coordinates, the local forces with respect to local nodal displacements via the stiffness matrix for the spring element. So these are a lot of information thrown at you. I encourage you to, I mean, this is quite simple as you will realize it. Go through this after the lecture and eventually this will be embedded in your brain. Nothing but matrix manipulation. Main idea is you move from a local coordinate system to a global coordinate system. You do it for the displacements and you do it for the forces. Yeah. So we have the force matrix in the local coordinate system, the displacement matrix in the local coordinate system. We have expanded now so that we make the stiffness matrix a square matrix, and we have expressed for a bar element in the local coordinate systems. It is the same equations that we used previously. What I have done here is we have simply expanded them to the total nodal degrees of freedom. Yes, because we are planning to construct the global stiffness matrix equation. Now, using equation which we derived here, that is equation 14 and equation 15, we can simply write, yeah, we know this is the relationship equation. We can use equation 14 and equation 15, which describes f hat and d hat. We can use equation number 2. What is equation number 2? Relates f hat is equal to, let's say, f hat is equal to k hat times d hat. If I'm not mistaken, this is equation number 2. Yes, f hat is equal to k hat d hat. We have now derived, we have expanded this obtained solutions for the f hat sign. We have expanded to the degrees of freedom, or we have considered the total degrees of freedom of the structure of the element. We have this equation now here, and d hat we have expressed here. So let me be clear. Where do we have f hat? Yeah, this is f hat, nothing but transformation matrix multiplied by the force matrix in the global coordinate system. D hat is equal to T times transformation matrix multiplied by the displacement matrix using the global coordinate system. Using this equation, you simply substitute f hat and d hat. What you would end up is getting this relationship, that is t hat f hat times related by this is f hat and this is d hat. So in order to get the calculate the force matrix, what you have to do is you have to multiply, take the inverse of t. Now you can invert it because all the matrices corresponding to inversions on the right hand side are square matrix, because we expanded them to the total degrees of freedom. So you simply multiply, take the inverse from the left hand side, and of course you take the inverse on the right hand side. So what you would end up is, I mean, if you multiply with the t inverse, of course this, what you would end up on the left hand side is f, and on the right hand side you would get a t inverse which is multiplied by the rest of the terms. So We can also show that. I will not show here. You can, if you want, you can go through it and look at the derivation. We can show that the inverse of this matrix is equal to the transformation matrix of this T matrix. This is the square matrix now. So using this explanation, or using this definition, you can express the force matrix is equal to T inverse now is replaced by T K times T times D. Quite interesting now. We are expanded into the global the degrees of freedom corresponding to the global coordinate system. Global forces is expressed via global nodal displacements, and what is remaining at the middle is the global stiffness matrix for an element. The global stiffness matrix for an element. So we have moved from the global stiffness matrix in the local coordinate system. Sorry, we have moved from the local coordinate stiffness matrix in the local coordinate system for an element to the element stiffness matrix in the for an element in the global coordinate system. Yeah. So equation 13, for example, you can use equation 13 and equation 16. That is equation 13 and equation, of course, equation 13, and of course we can construct equation 16, these two large equations, yeah, to obtain equation, let's say 18, that is the this matrix, the total global stiffness matrix for an element, which is given by equation 18 here. So once you do the math, what you would end up is you would get for an element the stiffness matrix in the global coordinate system is nothing but AED times L, material properties and also geometric properties, and you would end up is getting a symmetric matrix using which is expressed in terms of, you can see this is the same matrix, so we call it a symmetric matrix, and symmetric around the diagonal, of course. Yeah, and which is expressed in terms of cosines and sines. You would end up in getting, you can use equation 13 and 16, equation 13 and 16 to obtain this equation. You can substitute and you can check. Yeah, you can use equation this 13 and 16 in this expression, in this equation number 18 here, and try to get this equation. You would see that the stiffness can be summed up now, since you have expressed in this in the global coordinate system. Now you can sum up different elements to obtain the global total structure stiffness matrix for the whole structure using the direct stiffness method. So for each element, you have now defined the stiffness matrix in the global coordinate system. It's a matter of summing up to obtain the total structure stiffness matrix, and similarly you can sum up the forces applied for each element in the global coordinate system to apply to relate it to the global nodal force matrix, considering the whole structure. So this is the total structure stiffness matrix where all the components are assembled, which is expressed by the total nodal forces applied on the structure, total nodal displacements. Let's consider example 3. Let's call it an example 3.3. What you have to do is, for the bar element, of course, shown here, quite simple. A bar element where the local coordinate system is rotated anti-clockwise by 30 degrees with reference to the global coordinate system. And for this bar element, try to evaluate the global stiffness matrix with respect to the XY system, and assume the cross-sectional area and the length and the modulus of elasticity is given, and of course the rotation angle is given. What you need to first do is, since the rotation is anti-clockwise, we consider it to be positive, or the theta to be positive when it is measured from anti-clockwise or counterclockwise from x to x hat. We move from x to x hat. This is positive because it is counterclockwise. This is a sign convention that we will be using throughout this course. So theta is the angle of rotation. Cos and sine theta are cos 30 and sine 30 you can obtain by simply substituting these values, or you can obtain these values. Once you obtain this value, you can apply equation number, let's say, what is the equation number 19, to obtain the total stiffness matrix or the global stiffness matrix for this spring element, rotated bar element, sorry. Cross-sectional area, modulus of elasticity, the length of the element is given. So here we have used the imperial units, and of course what you would end up is getting a symmetric matrix. The symmetricity is given. You can see these two triangular shaped subdomains are symmetric around the diagonal element. Let's try to now apply the concepts that we learn and analyze a plane structure or plane structure made out of trusses. What is a plane truss? Plane truss is nothing but a structure which is composed of, let's say, bar elements or prismatic bar elements made out of linear elastic bar elements, which all lie in a common plane. Yeah, so they are not 3D, but they are laid in 2 dimensions, and they are also supported by frictionless pins. So they are connected by frictionless pins. So there are no reactions, so there are no bending moments or shear forces acting at these pin joints. So this is the intention. Yes. So we consider that they're subjected to loads acting on common plane, of course, and all loads must be applied at the nodes or joints, because we are at the moment we are not considering the distributed loads, which we will look at later onwards. But for the moment, nodal forces are applied either at joints or nodes. Keeping this in mind, let's look at this example, which is a truss assemblage, pin connected truss. You can see 3 elements, 1, 2, and 3, connected via pins, and we can use this notation 1, 2, and 3, and 4 to denote the nodes of the structure. And this structure is subjected to 10,000 pounds, length having 12 feet each. You define here the global coordinate system. What is your task now? For the task, for the plane truss consisting of 3 elements, which is subjected to a force of 10,000 pounds, which is applied at node 1, you are supposed to find the displacement at node 1 in the x and y direction, of course, in the global coordinate system. And let us assume that E and A and L of the, of course, the properties, the material properties, as well as the geometric properties for the truss are given. What do we do first? First, we need to write down the element stiffness matrices before we assemble, before we consider the total structure, before we consider apply the direct stiffness method to assemble the structure, we have to write down the element stiffness matrix for each element in the global coordinate system. Yeah, simple. This is just the one we just derived. So it is required to determine, let's say, the global stiffness matrix for each element. For this, we will be using the equation which we just derived, symmetric equation, which is nothing but an expression using the geometries or using the angle of rotation. So for each element, let's consider the angle between each element is theta. And if the global coordinate, let's say x-axis, and the local coordinate x-axis for each element have to be obtained. And whenever the angle is estimated, whenever the angle has a the local displacement, the local coordinate system has a anti-clockwise direction rotation, we consider it to be a positive angle of, if it is moved from if the movement or the rotation from x to x hat is anti-clockwise, we consider it to be positive. Right, keeping that in mind, let's try to find out the cosines and the sine as terms, because we have to obtain these all cosine sines, cosine squared and sine squared, as well as cosine sine terms, in order to determine this matrix, isn't it? So let's try to find out for each element these different terms. We have three elements. The most elegant way of doing this is to use a table. We have three elements. You can try it on your own now. You have three elements. Let's consider the first element. What is the first element? I will use three different colors for three different elements. First element. What is the angle? So based on the local coordinate system is along the bar. According to the global coordinate system, the x is defined in the horizontal direction like this. It has rotated 90 degrees, and since it is anti-clockwise, it is plus 90 degrees. For bar element 1, the rotation is 90 degrees. So correspondingly, the cos theta, sin theta, and the other terms can be determined. Consider element number 2. For element number 2, which is this element, what is the angle of rotation? This is the global coordinate system, and this is the local coordinate system. The angle has rotated by 45 degrees, and it is plus 45 because it is, we are considering it in the anti-clockwise direction. So that is why we have plus 45, and the corresponding terms can be obtained. How about 3? Element number 3. Element number 3 is nothing but the same element. So the local coordinate system, the local x and x hat sign, the x and the x hat now coincide with each other. So basically, the displacement, the rotation is 0 degrees. So correspondingly, you can find the remaining terms. So interestingly, how many number of nodes do we have in this problem? We have 1, 2, 3, and 4. 4 nodes. Each node has 2 degrees of freedom because it either can move in the x direction and y direction. So how many total number of degrees of freedom do we have? We have 8 total number of degrees of freedom in this in this system. So our elements should have, or our stiffness matrix should be 8 by 8 matrix. Yeah, keep that in mind before we move on to the next section. So the total stiffness matrix of the total structure should be an 8 by 8 matrix. So in order to apply the boundary conditions, as well as the displacement, the known displacement, and the known nodal forces of the structure, we need to construct an 8 by 8 matrix using, let's say, the element stiffness matrices, which we just derived, which we will be deriving now, which we'll be writing now. And for each element, How many nodes do we have? If we consider element number 1, okay, let's consider element number 3. Element number 3 has 2 nodes. Each node has 2 degrees of freedom in the x and y direction. So altogether, each element will have 4 degrees of freedom, meaning it is the stiffness matrix for each element would be a 4 by 4 matrix. Keeping that in mind, yeah, you can use for element 1, you can use equation number 1. You can use this equation number 1, and for element number 1, it is simply a times E divided by L, and you apply the corresponding cosine and sine terms, which is a 4 by 4 matrix here for each element. Now, in order to obtain using this table, you can apply the cos and sine terms and the corresponding terms to obtain this this matrix, which is a 4 by 4 matrix considering element number 1. Element number 1 corresponding to node number 1 and node number 2. Node number 1 and node number 2, element number 1. So because we are trying to use the direct stiffness method to construct the total global stiffness matrix, let's write down the corresponding displacements at the top column, top row rather. So here you can see d1x, d1y. So node 1, the corresponding components relating to node number 2 can be written like this. Similarly, for element number 2, we can write down the equations. We can write the total global stiffness matrix for element number 2 using the geometric data as well as the cosine, sine, and the corresponding terms. And you would end up in getting just try to substitute the values you use get in the table. These values here, which I have shown here for element number 2, and the corresponding nodal displacements are node number 1 and node number 3. So again, the displacements and in the x and the y directions, you can write it on the top. Similarly, for element 3, you can construct the global stiffness matrix. Now the corresponding terms for the element number 3 is the corresponding nodal displacements are d1x, d1y, d4x, and d4y, and this is the matrix once you substitute the corresponding values of the table. So now let's try to construct, or we try to find a common factor. What is the common factor? We can see that the modulus of elasticity, the cross-sectional area, and the length can be considered as a common factor and taken out from all the elements before we construct the total global stiffness matrix. And we can use this equation 2, 3, and 4, which are the element stiffness matrices for element number 1, element number 2, and element number 3. All of these matrices are 4 by 4 matrices. Why? Because each element has 2 degrees of freedom, 4 degrees of freedoms, that is 2 nodes. Each node has 2 degrees of freedom. So each element has 4 degrees of freedom altogether, 4 by 4 matrices. We have 3 4 by 4 matrices. Now we have to construct the total stiffness matrix for the total structure. We know the total structure has 4 nodes. Each node has 2 degrees of freedom. So the total global stiffness matrix will be 8 by 8 matrix. So now using these element stiffness matrices, and let's try to construct the total global stiffness matrix. For this, you simply write the K matrix. It's capital K because it's total global stiffness matrix. And assume now this matrix is totally empty first. First, you write down the corresponding displacements, d1x, d2. First node has 2 degrees of freedom in the x direction and y direction. The second node has 2 degrees of freedom, x direction, y direction. Third direction, similarly, you have 3 direction, and fourth, you also have the same 2 degrees of freedom. Same thing applies in the column wise. Now you apply the direct stiffness method. Do we have components which contribute to d1x and d1x? That is the elements which are corresponding to this location. Go through each matrix and try to find whether there are paths corresponding to these displacements at node number 1, node number 1 with one node where d1x relates to d1x. So here you can see, if we consider element number 1, yes, we have one element. Element number 2, yes, again there is d1x and d1x. Good, we have one. Element number 3, of course, we have d1x, d1x here. You can sum these three terms up. Yeah, did I miss one thing? D1x, D1x. Assume it to be 1 point. No, this is correct because this I have included the common factor now. That's the concern. Yeah. So you can add these three terms: 0.5, 1, and you would end up in getting 1.352. This is because that because of this common factor that for this case we have an additional square root of 2 underneath these terms. But try to get this idea. Try to go through each stiffness matrices for the element, and at the it is nothing but simply this is an 8 by 8 matrix. Simply add the corresponding parts, go through each component and try to apply the direct stiffness method and simply construct the total stiffness matrix equation. It's quite straightforward. So we know that the total global stiffness matrix, which is quite cumbersome, of course, which is 8 by 8 matrix. Now, since we have the total global stiffness matrix, we can relate it to the total structure, that is total global forces as well as total global displacements. Simply, we can apply the boundary conditions. K is given here in equation number 5. F matrix and D matrix, considering the total structure. So because we are considering total structure, we are writing capital F and capital D. Apply the boundary conditions. We know at node number 1, in x direction there is no force, but in the y direction there is minus. In the negative y direction there's a 10,000 pound force applying, so it's minus 10,000, and the rest are reaction forces which we would like to determine. What do we know when we consider the displacement vector, matrix? We know that at node number 2 and node number 3 and as well as node number 4 are fixed, so their displacements are 0. These are the boundary conditions which we know. So by applying these boundary conditions, we can selectively use elements and columns in the total stiffness matrix. So in this case, we can use the ones we can go from the knowns to unknowns. We can use the first and the second rows, and of course extract this stiffness matrix from our total stiffness matrix equation. This is these terms here. 1, yeah, and try to find the nodal forces or the displacements at node number 1 in the x direction. So in this case, you would get d1x to be positive. That means it moves towards the right hand side, and the y value you would get a negative direction, meaning based on the sign convention the movement will be downwards. So based on the components x and y components, you can now directly find the total displacements because you already know the components, the deviation or the deformations at each node. Okay, I think we covered a substantial part within this lecture. We almost, we were able to cover 3-dimensional, I mean, the total stiffness matrix using the transformation matrices. we were able to cover the two-dimensional problem. And there is more. The three-dimensional problem is the same as the two-dimensional problem, nothing different. It is an additional parameter, additional degree of freedom imposed. So I will maybe not utilize time to go through the three-dimensional problem, but I will upload my, let's say, lecture notes, or let's say some slides, which you can take your time and go through on your own. And if you have any questions or clarifications, we can clarify in the class. It is the same procedure, nothing different. It is an additional degree of freedom. So don't get confused, don't get complicated. Based on this additional degree of freedom, you will have an additional, let's say, terms coming into play, and you will have, let's say, a somewhat large, since we have additional degree of freedom, each node will have an additional degree component. So the matrix will be quite large when we are trying to solve it. Yeah, so I will upload this three-dimensional problem and you can solve it. Once again, just before I wind up, lot of information, of course, but nothing complicated, quite simple, lot of steps involved. Just go through each steps carefully, because this is the same thing we will be applying over and over again. Take your time, try to absorb the concepts that I have taught you in this class. When you do the lab class, this will be, of course, you will look at the problem via a computer program, and this will again will be helpful for you to thorough your knowledge.